I hope I get.
All right, welcome everyone.
Yeah.
Yeah.
Nice job, guys. Way to bring me in.
Yeah, Julius was the only one clapping. There we go. That's what I like it. All right, I know y'all are heartbroken. We're starting 10 minutes late, but take a moment, get hyped, get ready. Welcome to Return-Oriented Programming. All right, first of all, some announcements. Tomorrow, LACTF at 10 p.m. If you want some food, if you want to do a beginner-friendly CTF competition, if you want to help me and Sam do Pwn, that we're not the only ones, come tomorrow.
You know what, Pete or Richard, they are in Deloitte.
Yeah, Pete and Richard are gone, so you guys have to pull through, you know?
All right.
But yeah, come tomorrow. And here's your meeting flag. Sorry, I don't have an image. I don't know what XKCD is, but that's my fault.
Wait. It's okay. I will rectify this. Have one of mine.
Also, just a disclaimer. Before you start doing these challenges, make sure to uninstall Nix.
You will get roasted.
I refuse.
All right, I think everyone's got it. Okay. Okay, so just to review, you probably saw this the previous Pwn meetings, but this is what the memory looks like for the binaries we'll be working with. Last on Sunday we looked at the heap, but today we're going back to what we've looked at before, which is the stack and also the text section of the program, which has all of your instructions, functions, etc. And so at the start of Pwn 1, we talked about just like a basic buffer overflow, what we called a ret to win, where we just overwrite the return address to be a value. So there was a win function. We'd want to call that win function. And so we would send a bunch of bytes, overwrite the buffer, overwrite the saved base pointer, which doesn't really matter in this case, and then overwrite the return address to the address of win. So the stack would end up looking something like this with yeah. And we could do this because the gets function took like an unlimited amount of input. And so there were a few challenges after that where we removed the win function and we were like, okay, what do we do now? So does anyone know what we did now if the win function was removed? Yeah, you put shellcode on the stack. And this is called a ret to shellcode. So instead of overwriting the return address to point to a function, you'll need an address on the stack, and then you'll put your shellcode on the stack and then overwrite the return address to be the address of your shellcode. In this example, I put the shellcode like at the buffer, but you could also put it after return address too, and then address that. So, but yeah, this is a ret to shellcode. And so then, but this isn't the like actual like big brain like ROP stuff, you know, like where you're like, oh my God, I'm a hacker, you know, but that's what we're going to be getting to, right? So now there's a mitigation to this that you will see if you run like pwn checksec on the binary, you will see that there's something called NX enabled. And what NX is it just means that the stack is not executable. So any shellcode that if you try to jump to any shellcode on the stack and try to run stack stuff on the stack as if they were instructions, your program will segfault because the program now assigns permissions to different regions of memory. And so in this case, the stack is not executable. And this is part of a broader thing called WXRX, which is that like any region of memory shouldn't be both writable and executable. But so yeah, no more shellcode for you. So sad face for now, but not for long, guys. Not for long. Because does anyone have an idea of what we do now?
Well, it's a big binary. So I mean,
yeah.
There's probably symbols in the binary.
Yeah. Also, there's another thing. If we can't run shellcode, if we don't have a win function, maybe there's another thing that we can use. Yeah, or ROP. Okay, ROP.
Sorry.
Yeah, so this is what return-oriented programming is. It's a way to bypass this non-executable stack permission. So it's return-oriented programming is based off of the ret instructions. So you have these little chunks of code called gadgets. And what gadgets are is just a bunch of instructions, or maybe even just one instruction, or like two instructions, but the last instruction is a ret. And this is important that the last instruction is a ret, so then we can chain those together. So we can basically just keep returning to next gadgets. Now I'll show that like more in depth later. But so these gadgets will already be in the binary, or in some cases, well, in libc, which is linked to the binary. So we don't have to put shellcode anywhere. We don't have to write anywhere. We just have to jump to specific places in the binary to be able to execute what we want. And so at a high level, this is kind of what ROP is. So like you'd have these four sort of gadgets that you can execute, and you want to make b equals 3. So does anyone have an idea of how we would achieve that using these four gadgets? Yeah. Mhm. Yep. Yeah, exactly. So using those three gadgets like that, you can achieve, you can set b equal to a. So yeah, that's what it is. Now, that's at a high level. Now what it'll actually kind of look like is with instructions, each one ending in a ret. And so now with these instructions, can anyone say how you'd set RBX, the register RBX equal to 3? Yeah. Gadget 3 to make, and gadget 1. Yeah. So yeah, exactly. So you'd want to make,
Oh, yes. Gadget make RPX0. All right.
Swap with gadget 1, so we don't have RX0. Gadget 3 times to get RX equals to 3.
swap again. Yep, exactly. So this is how we can get RBX equal to 3. This is what return-oriented programming is kind of like in the abstract, I guess. But so now what our new exploit becomes is, instead of just returning that or overwriting that return address, we're still overwriting the return address. But instead of just overwriting the return address to be the address of just some sort of function we're trying to execute that's already in the binary or something, we'll put like the addresses of different gadgets that we want to execute sequentially. And due to the nature of the return instruction, which increments the stack pointer, that's a little bit like beyond this, but due to the nature, those gadgets will execute sequentially. And so we can do that to basically achieve some sort of RCE. And so here's a pretty basic example. It's pretty useful for the first ROP challenge, new ROP challenge though. So here's an example of like a pretty basic ROP chain. And so what we can do is we'll overwrite the return address to point to the gadget pop RDI ret. And so what will happen then is then the thing after the pop RDI gadget on the stack will go into the RDI register. And now when we call win, we'll have the RDI register set to what we want it to be. And at least for 64-bit x86, the based on the calling convention, the first 6 arguments of a function are use the registers RDI, RSI, RDX, etc. It's there. Yeah. Yeah, in 32-bit, it's a little bit different, but none of the challenges are 32-bit. But just in case you ever encounter, like you're doing a CTF and you encounter a 30-bit, 2-bit binary, like it's a little bit different the way you do ROP. Yeah, but in practice, there's usually not like just a win function sitting there with arguments or whatever. So most of the time, what you really are trying to do is you're trying to pop a shell. So basically just run bin sh like on their system pretty much. And so the way we can do that, there's a couple ways that are most common, but I'm sure there's other ways as well. But so there's exec ve bin sh null, which is also helpful for one of the ROP challenges. This is just a syscall, so you can set up the registers in the way that I explained on the previous slide, by using pop instructions or pop gadgets, and then you can use a syscall gadget to basically call exec v. And so if you can set the arguments properly, then you'll basically pop a shell. Yeah.
If they disable exec VE or like running other programs, what are other options to access the file system?
I have no idea. You know?
Yes. So in cases where you can't do exec VE, you'll have like a longer ROP chain where you'll usually do things like read, open, and write.
Oh, yeah.
That allows you to access files on the system, but then you kind of have to keep in mind like the file descriptors that you open, where you're reading memory to and where you're writing memory from.
Okay, yeah. So, okay, and then now, like, you might be wondering, like, how are we actually constructing these ROP chains? How do you find these gadgets in memory? And so, one way you can do it is you can just like object dump the binary and literally look for segments in memory that end with a ret instruction, or use this object dump command. And yeah, you can do that. And like, if that's fun for you, maybe take CS461. I've heard that you do have to do like ROP by hand in that class, but yeah. So, but most people instead, what they'll do is they'll use tools like ROP gadget to list gadgets in the binary, or you can even use ROP gadget to just generate a ROP chain for you that automatically pops a shell. So that comes in pretty handy a lot of the time. And then also Pwn tools and Ponybug. Well, actually Ponybug just uses ROP gadget, but Pwn tools has its own like ROP objects and you can list gadgets with that. Pwn tools, when you do it, beware, it will omit some gadgets it thinks are useless, but yeah, it's also useful. And then the last thing is one gadget. If you want like a lot of more information on that, there was more in the Pwn2 meeting, I think. But one gadget is basically you can find these like sort of magic gadgets that just pop a shell for you, something. So like there'll be a gadget that's like exec VE with bin sh, and you just have to make sure the registers are set properly. Some registers are set properly. But most of the time, these gadgets will be hard to find in the binary. They won't be in the like the binaries code itself. And so usually what we want to do here is we want to look for gadgets in libc instead, because libc is a giant file full of all your like standard library functions. And so if we have, and so there's going to be a lot of gadgets in there. And so if we somehow leak the address of libc, then we can leak the address where libc is linked to the binary. Then we can call gadgets from libc, which gives us lets us do a lot more powerful things. And so yeah, so the goal a lot of times is to leak a libc address and calculate the base address of libc, and then ROP from those addresses or gadgets in libc. And there's something called a libc database which helps you with calculating these offsets and such. Yeah, and okay, so now we'll talk about some things that sort of get in the way of ROP. One of them is PIE. We've talked about this before, I think in ROP 2 as well, but basically the addresses of the binary now no longer are at the same place every time. They'll be randomized. I think it's like 0x55 something will be like the sort of area where it is. But basically now functions are at different addresses each time. So you can't reliably, like if you're trying to jump to a gadget in a function or jump to a gadget in a binary, you don't necessarily have the address of those gadgets until you get a leak. ASLR is basically the same thing, but it randomizes the locations, like locations of the stack, the heap, randomizes libc, stuff like that. And so in order to access all these locations, address all these locations, you need to leak an address in one of those regions. So if I want to access a function, I have to leak an address of a of like main or something, and then it can calculate offsets based on that. Because the key thing here is that though the base addresses of each region are randomized, the offsets between the different like symbols, I guess, in that region are not randomized. So those offsets will stay the same. So if you can leak one address in a region, then you can use those offsets to calculate other addresses within that region. And here's an example just of how Hone Tools kind of works with this. So usually you like leak a libc address, and then this is how you can sort of calculate the offsets, calculate the base address by subtracting whatever the offset for whatever function you leaked or something, and then call system. So, and oh, another thing is a point of confusion a lot of times is you think you'll do everything right. Everything looks perfect and your code segfaults, and when you debug it, you can see that you're entering system and then segfaults. So the reason why is because libc expects your, like the stack, when you enter a libc function, it expects the stack to be aligned to 16 bytes. So if it's not aligned to 16 bytes, then it'll just segfault. So so an easy fix for that is you can add just a ret gadget at the start or before you jump into the function, just to align. It will just shift the stack by 8 bytes more. So it'll align it to 16 bytes. And yeah, here's some more resources just for learning and working with ROP. ROP Emporium is a good one, but yeah.
Where can I download shared objects for previous versions of libc?
Working on it.
You can use the two tools that are available are Pwnit or CTFmate. Both of those have the GitHubs available. What they'll do is when you run them in a directory with a program, it will try to, with a program and a libc that's given to you, it will try to fetch the libc with the debug symbols enabled, which is really helpful. If not, it will just use your default libc. Otherwise, you can just grab it from the Ubuntu Debian package manager and unpack it.
You can also, if they give you a Docker file, you can like create a just run the Docker image, the base image that they're using, see which libc is being used in that, and then Docker copy it back to your local system. Yeah, are there any other questions? All right. I expect them challenges to be solved, right? Solving the ROP challenges. Yeah.
First challenge is missing a flag file.
Really?
I got the shell and said missing flag.txt.
What? Oh no. Okay. Okay. I got it. Okay. Give me a sec. I'll fix it. That's my fault. I'll fix it.
What's the sample?
What? Yeah, okay. Come to LXCTF. Also, Jake's doing blockchain next week, so get ready for that. And here's the meeting flag again if you need it.